Did you do that one? Where did you show it? Is that, did you do it or? I thought class started at 4:20. I thought class started at 4:20. 4:05? It's 4:04.
This is a problem we sort of started fooling around with. There's a number of applications of PACCOMs. We ought to do 2 or 3 just to show the many ways in which PACCOMs can be used. So it's a case where you're going to try and carry out a gas-liquid reaction. Generally speaking, the gas is brought in. The gas A is normally a gas. It's carried in with in a gas stream, and its composition coming in is Y. So A is a gas. It's cup Y are the mole fractions of A on the gas side. X are the mole fractions of A on the liquid side. What happens is that some of this A, as it's coming in, is absorbed into the liquid. It reacts with a reactant in the liquid, which we assume to be in excess, which is generally the case. And so you convert what you absorb, or at least some of what you absorb, and then out goes stuff that's not converted, and out here goes stuff that's not converted. So F is the fraction that we feed. So 1 minus F then must be something like, well, Y out, V is lost, plus X out, L is lost, and Y in V is brought in. So we're going to specify F. This is given. And we'd like to, here's what we'd like to know. We'd like to know the height of a column to do the job. What is H to achieve F? And of course, we know how to do the absorption part out of the gas. Nothing's going on. Nothing's going on in the gas except the gas. The gas phase is the source of reactant A. The reaction takes place in the liquid phase. The liquid phase is the source of reactant B, and B is assumed to be in excess, so the reaction is essentially first order with respect to A. So A is the cross-sectional. We got a couple of A's floating around. A is the cross-sectional area of the column. Epsilon is the volume fraction of liquid. In the column. C is the molar density of the liquid, molar density of the liquid phase. So in a volume AdZ, say between Z and Z plus dZ, the column volume is AdZ. The liquid volume is epsilon AdZ. The amount of moles in that volume is C epsilon AdZ. That's the number of moles in the liquid in that piece of a column. So that's what those symbols stand for. So what is this exercise in mass balance by and large? So we begin. V, we'll assume dilute, of course. dy dz equals ky a y star minus y times a. That's the cross-sectional area, as always. All these symbols are as always. And of course, y star is mx. And I'm going to have L dx dz. I'm running this counter current as I have been all along, equals ky a y star minus y a. This is the rate at which x is changing as it flows down a column. It's the rate at which it's picking up solute. And we've got to account for the rate at which the solute is reacting. Well, we're going to say it's a first order reaction. You probably know enough about first order reactions to know that the rates of these things are written in terms of a rate constant k, whose dimensions are 1 by time. So I will write here k, my first order rate constant, x times that stuff there is what I want. So this and y star equals mx. These are my equations. I have two conditions. From here on, it's not a tough problem really. I'm bringing in y in, which is set, and I'm bringing in x in, which is 0. So this is known, and this is known to be 0. No a coming in here. No a coming in here. At the top of the column on the liquid side. So I got to do something with this. Now these y stars are of course mx. This is mx. So I got two differential equations here in x and y, and on the right hand side I notice they're linear. I notice they're homogeneous. All that's good. But I notice that I can't use my usual trick. So there's a number of ways that you can deal with this. A simple way to deal with a problem like this is simply to eliminate y. So I'm going to observe that I can write this. Well, I'm going to divide by. I'm going to divide by v, of course. I'm going to divide by L, of course. And I'm going to write this as dy dx. dy dz equals 1 over h over y mx minus y. I'm going to write this one dx dz equals 1 over h over y. This must be v over L. This must be mx minus y. And I'll simply give that group down there epsilon c k L over a new name, h. The dimensions of h are length. Well, the dimensions of k are 1 over time. The dimensions of h are length, just like h over y. So what I got here is 1 over h x. So how am I going to state my problem? In order to save a little writing, I will simply write my problem as dy dz equals ay plus bx, and dx dz is C y plus dx. A, B, C, and D are constants that are read right off of there. So I know them. So my problem is to solve this with y equal to y in at z equal to 0, x equal to x in equal to 0 at z equal to h. So I do what? The easiest thing to do with a problem like this, maybe even the least sophisticated thing to do, but nonetheless the easiest thing to do, is to eliminate y. So I will eliminate y. And I will get the following equation. D2x dz squared minus a plus d dx dz plus ad minus bc x equals 0. Second order, linear, constant coefficients. We know how to solve these. So we said, hey, we remember how this goes. I think in notation, it's been around for 1,000 years. You consider the quadratic m squared minus a plus d m plus ad minus bc equals 0. It's a quadratic equation. Has two roots. Two roots. We'll call them m1 and m2. So the two roots of this quadratic equation, of course, depend on the values of a and d and b and c. A and d and b and c we read off from our original model, so we know those. So we know m1 and m2. And then x goes like so. X equals a e to the m1z plus b e to the m2z. My job, of course, is to find a and b at this point. So my job becomes what is a and what is b. Now, in order to find a and b, I noticed that my boundary conditions involve x and y, sine y. So if this is x, then y is equal to 1 over c times, it appears that it's 1 over c times dx dz minus dx. So, I can calculate dx dz till the cows come home. I can multiply d by x, and so I now have a formula for y as well as a formula for x. They both involve the two constants a and b. So, what do I do? That's x. Y must be, okay, it's going to be m1 minus d over c e to the m1z times a plus m2 minus d over c times b e to the m2z. So here is x and here is y. If I knew the constants a and b, I would have them. So I say, well, you know, I got these two boundary conditions. One of them is that x at z equal to h is x in, which is 0. Tells me that a plus, tells me a e to the m1h plus b e to the m2h equals 0. This is one equation, A and B. The other one is y. Y is given there, and y at x equals to 0 is 0. So y at z equal to 0 equals yn, sorry, it's yn. So yn is this, it's a m1 minus d over c. That's 1 plus b m2 minus d over c. This 0 is known, this yn is known, two equations and two unknowns. I now have a and b in terms of h. Well, and all the constants of the problem. So all I've got to do, and I guess I have to evaluate y out. So I have to evaluate x out. So x out equals, that's x at z equal to 0. So it's a plus b. I now have x out in terms of h, and y out, so I just got to evaluate y, so it's a e to the, no, it's a m1 minus d over c e to the m1h plus b m2 minus d over c e to the m2h. So what do I have now? I have x out and y out in terms of h. Where do the h's appear? Well, here's an h appearing, here's an h appearing. There's also h's in here and h's in here. So now I say, boy, I have a condition that will determine h. It is that somebody assigns me an f, and I say 1 minus f is y out plus x, y out over yn, good. Y out, oh, plus, yeah, sure, why not? Y out plus L over V x out divided by yn. There's what you're looking at y out, you're looking at x out. This is a formula. Given an f, you find h. Of course, by far the easiest thing to do is to input an h. Then everything's a direct calculation, and you can get f, and you can decide, do I like it?
What do you mean by input an h?
Hmm?
What do you mean by input an h?
Well,
Guess
okay, look, let me remind you. I've calculated x out. It's just a plus b. H is hidden in here, h is hidden in here. You can see them hidden in there wherever I had this thing written down. I don't remember where I had it written down. Yeah, I must have had it. Oh, these two equations right here. Here we go. When you solve these two equations right here, you get a and b in terms of h. There's an h there. There's an h there. This is known, xn is known to be 0, yn is known. So these are equations for a and b, two equations and two unknowns, gives you a and b in terms of h. X out is a plus b, so that's in terms of h. Y out is a times this times h. This depends on h, that depends on h, this depends on h, that depends on h. Y out depends on h. So I have a complicated formula here where this depends upon h in a complicated way, this depends upon h in a complicated way, and I got an equation. Complicated function of h on this side, f on that side. You might want to convert, I don't know, 90% of the a. You might want to find the h to do it. Well, if you put in 90%, then this becomes 0.1. You got to solve this mess